Okay, what we're going to do is we are going to continue on from the test video, and we're going to look at a, excuse me, another heterogeneous equilibria reaction. So let's say we have tin 4 oxide reacting with carbon monoxide. That's in equilibrium. And if we look at the forward reaction, that would give us tin in the solid form plus carbon dioxide. Now once again, we always need to balance our reaction. So if we look 1 tin, 1 tin, 1 carbon, 1 carbon. But the oxygens, we have 3 on the left hand side and we only have 2 on the right. So let's get an even number. How about if we go with 4? So to get 4 over on the left hand side, I'm going to put a coefficient of 2 on front of carbon monoxide. Then I'm going to put a 2 in front of carbon dioxide, and everything balances out. Alright, so to find the equilibrium constant, K of C is equal to, remember it's going to be products over reactants, and I am going to scan the notes that I did yesterday with the test video. So K of C is equal to products, so concentration of CO2, since we have a coefficient of 2, concentration is going to be squared over the concentration of carbon monoxide squared. There is another way of finding the equilibrium constant. C stands for concentration. What if we were just given partial pressures of gases? We need to find the K of P. Well, to find the K of P is just like finding the K of C. We always take products over reactants. But in this case, we would take the partial pressures of the gases. So instead of using the brackets, we're going to use parentheses. So partial pressure of carbon dioxide squared over partial pressure of carbon monoxide squared. Okay, so nothing new. It's just instead of having concentrations, we have pressures. And there is a way to go from between K of C and K of P. And the way that we do that is we use this formula. K of P is equal to K of C times R times T, so our ideal gas constant times temperature, delta N. The way that we find delta N we take number of moles products minus number of moles of reactants. So let's kind of look at an example of this. Excuse me. Try to find one here. Okay. For the following reaction, K of C is equal to 9.60 at 448 degrees Celsius. What is the K of P? Okay, and the reaction that we're going to be using for this one is going to be one that we saw yesterday. So N2 gas plus H2 gas in equilibrium with ammonia. Now this reaction actually does have a proper name to it. It is called the Haber process. This is actually the reaction that put Germany on the map for being a chemical manufacturer. Alright, so let's kind of bounce this quickly. 1 3, 2. Alright, so actually I'm going to change this temperature. Let's go with something a little bit simpler. Let's just go with 300 degrees Celsius. Okay. So K of P is equal to, and we're using our formula up here, K of C, and that was given to us 9.60 times. Now the R value that we're going to be using for this is 0.08206 times our temperature. Now, temperature is 300 degrees Celsius, and with the R value, or our ideal gas constant, temperature has to be in Kelvin. So 300 degrees Celsius to Kelvin. .15. Now, delta N. Well, moles of product minus moles of reactants. Right-hand side we have 2 moles. Left-hand side we have 4 because we have a coefficient of 1 and a coefficient of 3. So 2 minus 4, -2. Excuse me.